It is not acceptable to use a step-down transformer in reverse. Transformers are designed with specific primary and secondary windings intended for a particular voltage transformation direction. Reversing this intended direction can lead to damage to the transformer itself and any connected equipment. In the scenario described, the transformer is originally designed to step down voltage from 480 volts to 208 volts. If used in reverse, it will attempt to step up the voltage from 208 volts to 480 volts. This can result in overheating and eventual failure of the transformer. Additionally, it poses a risk of damage to equipment connected to the secondary side due to overvoltage. The presence of a floating neutral on the secondary side introduces a significant safety hazard. In the event of a fault within the equipment connected to the secondary side, the fault current could potentially flow through this floating neutral and into the ground. This creates a dangerous shock hazard for individuals who might come into contact with either the equipment or the surrounding ground. The grounding of the case does not mitigate the floating neutral hazard. Grounding the case provides a path for fault current to return to the source, but the floating neutral still allows for a potential difference between the neutral and ground under fault conditions. To safely convert 208 volts delta to 480 volts Y, it is imperative to use a transformer specifically designed and rated for this purpose. Attempting to use a step-down transformer in reverse is highly discouraged due to the inherent dangers involved. Using the incorrect transformer configuration could result in immediate equipment damage as well as long-term electrical grid instability. The transformer's core is designed to operate at a specific magnetic flux density for optimal efficiency and to avoid saturation. Operating it in reverse can cause the core to saturate, leading to increased magnetizing current, heat generation, and potentially premature failure of the insulation. The insulation within the transformer is also designed to withstand specific voltage levels between windings and to ground. Exceeding these voltage levels, as could occur when operating in reverse, can lead to insulation breakdown and short circuits. Furthermore, the tap settings on the transformer are designed for a specific input voltage range. Using the transformer in reverse can cause the output voltage to be outside of the acceptable range for the connected equipment. Regarding the floating neutral, it is important to understand its behavior. In a properly grounded Y system, the neutral is connected to ground at the service entrance, providing a low impedance path for fault current to return to the source. This allows overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and clear the fault. However, with a floating neutral, there is no intentional connection to ground. This means that the neutral voltage can drift to any value relative to ground, depending on the unbalanced load in the system. If a phase to ground fault occurs, the fault current will be limited by the impedance of the connected loads and the grounding impedance of the system. This can result in a much lower fault current than in a properly grounded system, which may not be sufficient to trip the overcurrent protection devices. The National Electrical Code, or NEC, provides specific requirements for grounding and bonding electrical systems. Section 250.20 details the systems that are required to be grounded, which includes Y-connected alternating current systems where the neutral is used as a circuit conductor. Section 250.24 outlines the requirements for grounding the neutral conductor at the service entrance. Section 250.4 provides general requirements for grounding and bonding, emphasizing the importance of creating a low impedance path for fault current to return to the source. Ignoring these requirements can lead to serious safety hazards and code violations. Now let us dive into some additional information. Firstly, impedance matching is a factor. Transformers are designed with specific impedance ratios between the primary and secondary windings. When operated in reverse, the impedance ratio is inverted, which can lead to impedance mismatch with the source and load. This mismatch can cause voltage regulation problems, increase current draw, and reduced efficiency. Secondly, harmonic distortion can arise. Operating a transformer in reverse can exacerbate harmonic distortion problems in the electrical system. Transformers are designed to minimize harmonic distortion under normal operating conditions, but reversing the voltage transformation can introduce or amplify harmonic currents, leading to overheating of equipment and potential damage to sensitive electronic loads. Thirdly, core saturation is an issue. A transformer's core is designed to operate within a specific range of magnetic flux density to minimize core losses and prevent saturation. Operating a transformer in reverse can cause the core to saturate, leading to increased magnetizing current, excessive heat generation, and potential damage to the transformer. 4. Insulation breakdown can occur. The insulation within a transformer is designed to withstand specific voltage levels between windings and to ground. Exceeding these voltage levels, as could occur when operating the transformer in reverse, can lead to insulation breakdown, short circuits, and catastrophic failure of the transformer. 5. Voltage regulation problems are also possible. Transformers are designed to maintain a relatively constant output voltage under varying load conditions. Operating a transformer in reverse can cause significant voltage regulation problems, with the output voltage fluctuating excessively as the load changes. This can damage or cause malfunction of connected equipment. 6. There is increased risk of ferroresonance. Ferroresonance is a complex phenomenon that can occur in electrical systems containing transformers, capacitors, and inductive reactances. Operating a transformer in reverse can increase the risk of ferroresonance, which can lead to overvoltages, excessive currents, and equipment damage. 7. There are specific design considerations in play. Transformers are designed with specific cooling systems to dissipate heat generated during operation. Operating a transformer in reverse can alter the heat distribution within the transformer, potentially leading to overheating and premature failure of the cooling system. 8. Potential exists for misapplication of overcurrent protection. Overcurrent protection devices, such as fuses and circuit breakers, are selected based on the transformer's rated current. Operating a transformer in reverse can result in misapplication of these devices, potentially leading to inadequate protection against overloads and short circuits. 9. There are code violations to be aware of. Using a step-down transformer in reverse can violate electrical codes and standards such as the NEC and applicable local regulations. These codes are designed to ensure the safety and proper functioning of electrical systems. Violations can result in fines, penalties, and potential liability in the event of an accident. 10. The nameplate data provides proper ratings. The transformer's nameplate provides critical information about its ratings, including voltage, current, frequency, and impedance. Operating a transformer outside of these rated parameters can lead to equipment damage and safety hazards. Always consult the nameplate data before installing or operating a transformer. It is crucial to always consult with a qualified electrical engineer or electrician to ensure that electrical systems are designed, installed, and operated safely and in accordance with applicable codes and standards. Now consider more scenarios. In a scenario where a 208-volt delta system needs to be connected to a 480-volt Y system, a properly designed step-up transformer should be used. This transformer will have the correct voltage ratio and impedance characteristics to ensure safe and reliable operation. Additionally, it will be designed to handle the specific load requirements of the connected equipment. The NEC provides guidance on selecting and installing transformers for various applications. For example, Section 450 covers the installation requirements for transformers, including clearances, ventilation, and overcurrent protection. Section 310.15 provides guidance on conductor ampacity, which is essential for ensuring that the transformer is properly protected against overloads. In addition to using the correct transformer, it is also important to ensure that the grounding system is properly installed and maintained. A properly grounded system will provide a low impedance path for fault current to return to the source, minimizing the risk of electric shock and equipment damage. Section 250 of the NEC provides detailed requirements for grounding and bonding electrical systems. These requirements cover everything from the size and type of grounding conductors to the methods for connecting grounding electrodes. Following these requirements is essential for ensuring the safety and reliability of the electrical system. Now consider the consequences of improper transformer application. Using a step-down transformer in reverse can have serious consequences, including equipment damage, fire, and electric shock. In some cases, the transformer may simply fail to operate properly, resulting in reduced efficiency and performance. In other cases, the transformer may overheat and catch fire, posing a significant safety hazard. If the transformer is not properly grounded, it can also create a shock hazard, potentially leading to serious injury or death. In conclusion, it is never safe to use a step-down transformer in reverse. Always use a transformer that is specifically designed for the intended application and ensure that the grounding system is properly installed and maintained. Consulting with a qualified electrical engineer or electrician is crucial for ensuring the safety and reliability of electrical systems. Always adhere to the NEC and other applicable codes and standards to minimize the risk of accidents and injuries. Using the correct transformer is not just a matter of convenience, it is a matter of safety. The consequences of using the wrong transformer can be severe, ranging from equipment damage to serious injury or death. Taking the time to select and install the correct transformer is an investment in safety and reliability that will pay off in the long run. The grounding of electrical systems is crucial for safety and proper operation. Proper grounding ensures a low impedance path for fault currents, allowing overcurrent protection devices to quickly trip and clear faults, minimizing the risk of electrical shock and equipment damage. The NEC provides comprehensive requirements for grounding and bonding, covering everything from grounding electrode systems to equipment grounding conductors. Ignoring these requirements can lead to serious safety hazards and code violations. Always consult with a qualified electrical professional to ensure that the grounding system is properly designed and installed. Remember that electricity is a powerful force that must be treated with respect. Always follow safe work practices and consult with qualified professionals when working with electrical systems. Taking the time to understand the principles of electricity and the safety requirements can help prevent accidents and injuries. By following these guidelines, we can ensure the safe and reliable operation of electrical systems for ourselves and others. Proper transformer selection and application is essential for the safe and efficient operation of electrical systems.